We're going to look at differentiating exponential functions and how we use those in applications. So, with exponential functions, it pretty much stays the same as e to the power kx, but you take the power down, but you don't need to do any subtractions or anything. So, part A, find the derivatives of all these. So, like I said, write out the original and just write out the multiple in the front, and that's it. Pretty simple, right? Part B, we're doing a quarter times 2 e to the power 2x plus, now if you follow the rule here, if f of x is equal to e power dx, and f dash of x is g dash of x times e to the power gx. So that means we get 2x e x squared. Then simplify. If you're not sure as to why that happens, we'll be explaining that in a bit. This is called the chain rule. If you want to, you can skip ahead to the chain rule video, which will be up there soon. Or by the time you watch this, it's probably up there already. Alright, part C. We need to, because we have fractional bits, we need to separate it into separate fractions, like so. Then write it out with negative or positive powers, so long as it's on the top line. So the first one is a 1, those are the same. Then we have e to the power of x minus 2x minus e to the power negative 2x. Oh, whoops, I wrote that wrong. That should be a y. My bad. Just noticed. Now we take the derivative. So 1 simplifies to a 0. We then get negative 3 e negative x plus e negative 2x. And then d. Expand it out first, unless you've learnt what the product rule is. Alright, not the product rule. The other expansion. Anyway, that one you can use for a later time. Right now, we'll just expand it. So have e x all squared, which is e to the power 2x, minus 4 ex plus 4. Take the derivative, then we get 2e 2x minus 4e to the power x. Okay, determine gradient of a tangent to the curve y equals to e to the power of negative x at the point where x is equal to 1. So the x is negative e negative x. Then when x is equal to 1, sub it in, go forward. What? And because it's a power of negative 1, it's just 1 over e. B. Determine the equation of a tangent. So we have gradient, so just a y minus. Oh, we need to actually find what y is first. The y is e to the power 1. 1 over e. Then for the tangent, we have y minus 1 over e equals to negative 1 over e x minus 1. So then you have negative x over e plus 1 over e plus 1 over e. So then y is then equal to negative x over e plus 2 over e. Alright, then if we want the perpendicular one, We then need to use negative 1 over negative 1 over e. That then gives us negative 1 divided by negative 1 over e. So keep the first one, change the second one to a times, and then flip it. Negative negatives cancel, and we're left with an e. So then we just do y minus y1, which is 1 over e, equals to e times x minus 1. And then we have ex, not e to the power of x. Then add the 1 over e over. I might just put the e at, no, I shouldn't actually. I should put the e in the front because it's technically a number. So ex plus 1 minus e squared over e. Alright, so normally with exponential functions, we look at populations. In particular, this one's looking at number of bacteria. So here we go. How many bacteria are initially present? Something to 0, that's the initial value. Should give you 2000 because anything above 0 is 1. If you're not sure what I mean, you have 0.3 times 0 there. So then give you a 1. So that's 2000. How many bacteria is the nearest whole number present up to 10 seconds? 7 10. That gives us 2000 times e to the power 0.3 times 10, which then gives us 2000 times e to the power 3. That then gives us 40,071. Let's see, at what rate is the bacteria population multiplying? So because right, we need to find the derivative, which then gives us 2000 times 0.3 e to the power 0.3. That'll give us 600 e to the power 0.3. 710 gives us 600 e to the power 3, which is then equal to 12,000 and something. I did it just before, and I decided to re-record it because I said something wrong. So 12,051. So that's how many bacteria are multiplying per sec. How many bacteria are being added on per second at that time.